And so today we're going to talk about the cross-channel momentum balance. So if you remember, when we put our classroom in the context of the reference frame, the y-axis was over there, right? The x-axis is here, and the z-axis is vertical. So what we've been looking at so far is the motion in this direction, in the direction along the x-axis in an estuary. And we have proposed several frameworks, dynamical frameworks, under which we can study different types of estuaries. We said that for a typical partially mixed estuary, the dominant dynamics is between the pressure gradient and friction, right? So the flow would consist of a near surface outflow and near bottom inflow. And then we said that for fjords, then we'd have the pressure gradient being balanced by advection. And for salt wedge estuary, the pressure gradient would be balanced by advection and interfacial friction, right? And what other momentum balance did we cover? We covered 4 types of momentum balance. Wasn't it? Or what else am I missing? Pressure gradient balance by no? Am I wrong? We just covered those 3. Oh, right. Because we said that the friction can be in the case of rivers, in which the flow is unidirectional. The flow is driven by a sea level slope, not by a density gradient only. It's a homogeneous situation. And the other situation of pressure gradient being balanced by friction is that of estuaries, right? Where we have the pressure gradient driven by slopes, but also by density gradients, and balanced by frictional effects, right? Something that I didn't mention that is becoming increasingly evident with recent research is that the friction in typical shallow, partially mixed estuaries, the friction comes mainly from bottom drag. There's very little internal friction among the layers. All the friction is produced by the interaction of the flow with the bottom. Now, under very stratified conditions like the Fraser River or in a salt wedge estuary, then you might have some interfacial friction, interfacial mixing. So maybe in those cases, most of the mixing comes from interfacial interaction rather than with interaction with bottom friction. So that's a very hot issue at the moment, because some people think that all of the friction comes from bottom friction, but there are some new schools of thought that are proposing that in cases of stratified systems, a lot of or most of the friction comes from interfacial friction. So that's a big question that needs to be resolved still in the study of estuaries. So again, as I was saying, we're going to study now the momentum balance in the across estuary direction. So in the context of our classroom in this direction. So what would you think happens? Well, first let's look at that's the lateral momentum balance. So conceptually, let's try to think what would happen to this estuary flow. Let's suppose that we have near surface outflow and near bottom inflow. What's going to happen to this exchange flow, vertically sheared exchange flow across in that direction? What's the momentum balance? What do you think the momentum balance is? Any idea? Do you think the Earth's rotation will be important? Well, if the Earth's rotation is important, what's going to happen to the outflow? The outflow will be leaning toward the right, so it's going to go on that side of the room. And if the inflow is affected by rotation, it's going to lean preferentially on this side of the room, on the roof. So you'd have more some vertical shear, but also some lateral shear, because the strongest outflow would be located on that wall, and the strongest inflow will be located along this wall and along the bottom. So if we assume that that's what happens typically, or for the sake of our framework to study estuaries, if we start with that framework, what do you think are the assumptions in that lateral momentum balance that we're showing? Huh? Steady, right? So the first term over here, this term can be eliminated. Steady flow. How about this term? This term, we can assume that the flow is linear, so we can neglect the advective term. And we can also assume that there's no friction, that the momentum balance across the estuary is frictionless, no friction. So these three terms, 1, 2, 3, disappear. So we're left out with what? The pressure gradient being balanced by Coriolis. Okay, so how do we call that momentum balance? Pressure gradient being balanced by Coriolis. Some of you know, but some of you might not because you haven't taken physical oceanography, or maybe you've taken geophysical fluid dynamics somewhere else. But the balance between pressure gradient and Coriolis is called, right, geostrophic. That's a geostrophic balance. And schematically, we could visualize it in that cartoon. We're looking into the estuary. So this is the axis across the estuary, and we're looking into the estuary. So we have a surface outflow. The water is coming toward us right here in the upper layer, and in the lower layer, the water is going away from us. So preferentially, under the influence of rotation, this outflow will be strongest right here, and that's why the surface elevation is tilted like that. So that's in geostrophic balance, that surface elevation. And then the interface, the level of no motion, where there's zero flow, net flow, where the vertical shear is strongest, because we have outflow here and inflow here, is tilted also, and it's in geostrophic balance. So using the geostrophic approximation, we can determine how much this tilt will be and how much that tilt will be. Okay? So again, we can simplify that momentum balance by assuming that the pressure is given by the hydrostatic pressure of the upper layer plus the hydrostatic pressure of the lower layer, where ρ1 is the density of the upper layer and h1 is the thickness of the upper layer. And then ρ2 is the density of the lower layer and h2 is the thickness of the lower layer. So this is the total pressure throughout the water column. So in the lower layer, if we look at the geostrophic balance in the lower layer, we have pressure gradient balanced by, what is that? What is that term? Coriolis. Remember what that F means? What does that F mean? We covered it in the review early on. That's the Coriolis parameter, right? And what are the units of the Coriolis parameter? Yes, time to the -1, second to the -1. So remember, we're talking about the momentum balance per unit mass per unit time. So we're talking about accelerations. So on both sides of the equation there, we have to have acceleration. So the units of u are meters per second. So the units of f should be 1/second to get meters per second squared on the right-hand side. So remember, the Coriolis parameter depends on what is the only variable in the Coriolis parameter. It depends on latitude, right? So the closer to the equator, the smaller the Coriolis parameter, the larger it'll be larger as you get closer to the poles. Okay, so we're expressing the geostrophic balance in the lower layer like that, the pressure gradient, total pressure gradient with the density of the lower layer normalized by the pressure density of the lower layer equals the Coriolis acceleration in the lower layer. So we can express the pressure in terms of this total pressure. So the Coriolis parameter is going to be equal to the pressure gradient here. But the pressure gradient now expressed in terms of, again, the pressure as given by the thickness of the upper layer and the lower layer. That's given there. So now we are looking at the gradient, how much the upper layer changes across the estuary and how much the lower layer changes across the estuary. So this is effectively the pressure gradient. And this whole thing is the geostrophic balance in the lower layer. So we haven't done anything yet. So now if we look at the upper layer, what's the geostrophic balance in the upper layer? The Coriolis acceleration can be written straightforward. That's the Coriolis acceleration. And the pressure gradient can be written in terms of the slope, the sea level slope, across the estuary. So we have this row goes with that row. And we can express the slope, d eta dy. So this d eta dy, the change of eta with respect to y, can be expressed in terms of the total water column, H1 plus H2, with respect to y. So it's the same thing. So now we can represent this geostrophic balance that's written up here in terms of both H1 and H2. So we've moved the G to the denominator here, and the minus sign we moved it over here. And now we have this Fu over G as a function of the sum of the two slopes of the layer. So that's again the geostrophic balance in the upper layer, and we can rearrange in terms of dH1 over dy. We just go for dH1 over dy, and we have this one plus that one. So in the lower layer, we had expressed that the geostrophic balance could be like that. This is the geostrophic balance in the upper layer, the geostrophic balance in the lower layer. Let's write them up again. So we're okay, right, that this term is the geostrophic balance in the lower layer, and this is the geostrophic balance in the upper layer. So notice that we have dH2 dy in both equations. So we can solve for one of those, for dH2 dy actually, we're going to do. So we express dH1 dy, this one is given by this. So for the lower layer, we use the geostrophic balance in the upper layer. So we substitute the value of dH1 dy over here, and this is what we get. Here's Fu2, 1 over rho 2, rho 1g times dH1 dy, which is Fu1g, and dH2y. And then this term is the same as that. Okay? So then what do? Then we try to group the dH2 dy, because that's what we're looking to see what the slope of this interface is. The slope of the level of no motion, which is dH2 dy. So we group the dH2 dy. We have one here that's multiplied times rho 1g, that's where it shows. And then this one is multiplying rho 2g, so that's where it goes. This one with plus and this one with minus. Okay, so, and then we have this term and that term, and we have this g goes with that g, so we have rho 1 Fu1, which is right there, and then we have rho 2 is moved over here, so we have rho 2 Fu2. So we solve for dH2 dy, and straightforward. You can see that the slope of the level of no motion is a function of mainly 4 variables. Which are they? The flow in the upper layer, the density of the upper layer, the flow in the lower layer, and the density of the lower layer. Right. So how much is that interface going to tilt? Depends on the strength of the flow in the upper layer and the flow in the lower layer, and the density of the upper layer with respect to the lower layer. So this is called Margulis relation. And again, this allows us to estimate or get a rough estimate of the interface of the two layers under geostrophic motion. So again, that's the restriction here, that you're assuming that you have a geostrophic balance across the estuary. We'll learn later that it might sometimes that might be a good approximation, but sometimes it isn't. In what cases will it not? Remember, you wrote a summary about Pritchard's paper where he looked at these issues that we're talking about. If you notice, he proposed, right, that along the estuary the balance was between, what was the dynamic balance? What did he propose in his paper? You don't want to say, or you don't remember?
The printing was really bad. You really couldn't see the words, no.
But you got to write the abstract. You got to summarize the paper.
Didn't it occur in mid-depth usually?
Right, but what is the dynamic? He proposed. I think he was the first to propose a dynamic balance along the estuary and across the estuary in that paper of the dynamic structure of a coastal plain estuary. It's what we talked about last time. What is it? What's the dynamic balance in a partially mixed estuary? Pressure gradient balance by friction. If you remember, that's what Pritchard said with his observations. And also he showed a table in which he calculated each different terms in the momentum balance. And he showed that those two are the leading order term. And then for the lateral component, for the across estuary component, he did the same thing. Remember? And he proposed, what kind of balance did he propose? He proposed a geostrophic balance across the estuary. But if you remember well, he calculated the frictional terms too. And even though the frictional terms were on the same order of magnitude as the Coriolis term, he said that they were small. Right? So that was tricky because his frictional terms were sizable. So effectively, his data showed that there was no geostrophic balance, but he said that there was. I don't know if you caught that. But go back and look at it after this class. Go back and look at his table, the last table that he showed, and look at the frictional terms. And you'll see that the frictional terms are smaller than the Coriolis term, but I don't think you can neglect them completely. So again, we'll come back into this when we talk later in the course about bathymetric effects, and we'll discuss this in more depth. So the point where we were, so that I got off topic a little bit here. I was saying that the slope of the interface can be calculated if you assume that the momentum balance is geostrophic across the estuary. And that's a relationship you would use if you know nominal flows in the upper and lower layers and densities of the upper and lower layers. You'll be able to calculate the slope, the theoretical slope. And we'll do that in an example later on today. So that's the Margulis relation. So that's for the upper layer. How about that's for the lower layer, the Margulis relation. How about the slope for the upper layer? What would you do? Well, you follow similar procedures, and you take the geostrophic balance in the upper layer, which is this one, and you rewrite it here, and then rewrite dH2 dy in terms of the Margulis relation, which is given by this. Notice that now I've written delta rho as rho 2 minus rho 1. So again, this is the same. This is the geostrophic balance in the upper layer, but now expressing the dH2 dy in terms of the Margulis relationship, which is this one. So now, we can simplify these two terms, but first we need to note that delta rho equals rho 2 minus rho 1, which is the same as if taking delta rho as which is the same as if saying 1 plus rho 1 over delta rho equals this one, delta rho plus rho 1 over delta rho. So 1 plus rho 1 over delta rho equals this, and delta rho is rho 2 minus rho 1. So we have minus rho 1 plus rho 1 leaves us with rho 2 over delta rho. So the main point here is that 1 plus rho 1 over delta rho equals rho 2 over delta rho. This is what we're going to use up here because we're going to factor F over G delta rho here, and we'll use this relationship down here. So now we can say that we can again group these two terms, FU1 over G, which is FU1 over G times 1 plus rho 1 over delta rho. So these two terms are these two, and then this term comes here. But we know that 1 plus rho 1 over delta rho is rho 2 over delta rho. So this thing equals FU1 over G times rho 2 over delta rho plus this term here. So now we factor F. Notice that both terms have F over G delta rho over rho 2. I mean, this rho 2 here. So G times delta rho over rho 2 would be G prime, which is what we have here. So the factor, again, we have factor here F rho 2 G delta rho, which is the same as F over G prime. And we have this U1 with the negative sign, which appears here, and this U2 with the positive sign that appears here. So what we have is that pH1 dy, the slope of the upper layer, equals that. It's just a function of the vertical shear between the lower layer and the upper layer, and this G prime. This G prime we said was what?
Internal way.
Not yet. No, G prime H is the square root of G prime H is the speed of the long internal wave, right? Yeah. I hope you said it this morning when you woke up. You did? Good for you. But what's G prime? When you say square root of G prime H, you have to know what G prime H is.
It's the density difference multiplied by the gravity.
Right. Divided by, normalized by the density. Right. So and that's called the reduced gravity. And you know why it's called reduced gravity, right? We discussed that. Because you're multiplying G times delta rho over rho. And usually delta rho over rho is on the order of what? If delta rho is order 1, and rho is order 10 to the third, 1 over 10 to the third. So you're multiplying G times 10 to the minus 3. So that's why it's reduced gravity, the G prime. Okay? Probably that has to be part of your morning sayings. So when you wake up every morning and you say square root of G prime H, think about what G prime is also. Okay? Remember, G prime is reduced gravity. And it's reduced because you're multiplying gravity times a very small number. Don't forget tomorrow. Don't forget tomorrow. So you have those two expressions for the lower layer and the upper layer using geostrophy. So notice that with the flow in the upper layer and the flow of the lower layer, and the density of the upper layer and the density of the lower layer, we can determine the slopes, the sea level slope, because the sea level slope is dH1 dy plus dH2 dy. That is the sum of these two. So all you need are these four variables to gain some insight into the dynamics of the system across the estuary. Now, to illustrate these concepts, we're going to use some numerical results. We might not be able to see this if I animate it. So let's see. Oh yeah, I see it here beautifully. Okay, that's okay, because I thought about an alternative way. Our friends in Korea can watch the PowerPoint presentation separately, or I'm going to show it here on a different monitor. I'm going to show the animation here on a different monitor. As it loads. So what we're going to see here is a numerical simulation of an idealized situation. This is the coastline. This is the coastline. So this was done emulating the lower Chesapeake Bay. So this is a peninsula, and this is a cape. And what we have here is light water, fresh water, and salty water. this is the upper layer and this is a lower layer. So initially, this fresh water is separated by a partition from the salty water. So when you release the partition, what happens? The light water will adjust on top of the salty water. The salty water will tend to intrude. So let's see if that's what happens. So notice what happens in the upper layer here. The low salinity water, because of the Earth's rotation, goes this way, and then it goes around, hugging the coast, the right coast, and then goes out of the estuary and keeps hugging the coast and goes out like that. Do you understand what's going on? Do you follow? Or are you lost with coastline? And who's lost? Because if somebody's lost, it means that more than one.
I just want to check on the Coriolis and why the Earth's irrigation, why the lighter water or the less dense water goes to the left side, and then the more dense water, I guess, goes to the right.
Yeah. Well, you can see here that this is the lower layer, so the heavy water is intruding more on this side, on the right side, than on the left side, the lower layer. So it's coming back to our classroom here. This water here, this outflow right here is as if it was hugging that.
Why does the less dense water want to hug the left side or that side?
So if you don't have rotation, the light water will tend to go out like that, and the heavy water will come in. Right? But with rotation, the outflow will lean over this side and go like that. And the same way that near the bottom, the water will come like this, and then because of rotation, it's deflected to the right. It hits the wall, and it can go. It can just go down the pressure gradient, right? Goes hugging the wall like that. Right? Any other questions about that? So anyway, this illustrates then the adjustment of light fluid and a heavy fluid under the influence of rotation. So this adjustment is nearly geostrophic, as we will see. This is a numerical simulation that has all the terms in the momentum equation. So if we look, we can look in detail at. Well, you look at it a few more times. We can look in detail at fixed images in a minute. Okay, so that's enough. Enough show. Now we go and see and look at fixed images. So we have the near surface layer here on this side, the near bottom layer here, and we have at different times at 10 days after adjustment, 20 days, and 30 days. So look at the surface only for a moment. So you can see I think you can see the arrows. Can you see the arrows depicting the flow here? They go like this and like that. So what is this that we see here? Why do we have this bulge? This is getting ahead also of the game in the course, but this is a plume of light water coming out. You've seen plumes of...
Is that at the surface?
At the surface, right. And again, this is at 10 days, 20 days, 30 days at the surface. So you can see how the bulge of low salinity water forms as the fresh water comes out of the estuary and then forms coastal current as it propagates down the coast. All right, and in the lower layer you have the high salinity water being asymmetrically distributed. The water is not deep enough to create a clear two-layer circulation, but still you have higher salinity water here near the bottom than here at the surface. Okay, so now the reason I show this example is because we want to see how close to geostrophic balance the exchange flow is. But the exchange flow right here at a transect right at the mouth, if I look at a transect right at the mouth, I can see the exchange flow and see how close to geostrophic balance it is. How would you determine how close to geostrophic balance it is? Obviously by using the Margulis relationship that we just saw. So Let's see if we can do that. All right, so now we're sitting in the ocean looking into this idealized estuary. So the light outflow is coming on this side. There's different shades of gray denote different salinities. So the lighter the water, the lower the salinity. Sorry, the lighter the water, the higher the salinity, and the darker the shade, the lower the salinity. So this is fresh water up here, fresher water. All this is fresher water. And then these lines are contours with isotachs, contours of flow. Sorry, contours of flow. And negative means coming out of the screen toward you. And all this region is inflow, going away from you into the screen. Right, so after 10 days, the outflow is concentrated in this area. After 20 days, the outflow is concentrated in this area. And after 30 days, the outflow is all around here. And the inflow is here, the inflow is here, the inflow is here. Notice that the outflow is concentrated over a very narrow area. That's because of the Earth's rotation. Okay, so let's see what the observed slope. If we look at this after 30 days, which is closer to being in steady state. Remember, for geostrophic balance to develop, you need the dV dt equals 0. So you can see that the dV dt keeps progressing from here to here and from here to here. So at this point, the dV dt is getting close to 0. And the slope of this is the slope of the interface. This is the one that we can compare to Margulis' relationship. This is supposedly the slope of the level of no motion. That's what we were talking about, the zero flow. So as you can see, over 10 kilometers, it changes by approximately 2 meters in 10 kilometers. So that's the observed slope. Do we agree on that? So the slope is 2 over 10 to the 4th, so that's 2 times 10 to the minus 4. That's the observed slope. Now, we use the Margulis relationship to calculate what kind of slope we get. So I use, for that numerical simulation, I used a Coriolis parameter of 8.8 times 10 to the minus 5. What are the units again? Second to the minus 1. The nominal speed for the upper layer is 8 centimeters per second. So if you integrate over this, the average over this whole section, you have 10 centimeters per second, 5. So we could say 8 centimeters per second. And for the lower layer, we could say 2.5 centimeters per second. The density of the upper layer is 1,020 what unit? Kilograms per cubic meter. So that's the density of the upper layer, the density of the lower layer. So if we use these values and plug them in there, we get the h2 dy, which could give us a slope. And what we get is 2.3 times 10 to the minus 4. That's pretty close. I mean, that's amazingly close. So we can safely say that the lateral momentum balance at this time is geostrophic, essentially geostrophic. I'll show you some examples later where it is not. But
what about from 110 all the way to this way?
right. Well, what happens there? So the slope is much weaker, but the flow is also much weaker. So I don't know. It'd be a matter of seeing. And also the fact that it's sloping in the opposite, with the opposite sign, it means that perhaps geostrophic balance is only valid within this area and not anymore right around here. So that's a good question. So the geostrophic balance will predict a slope in that direction like that, positive slope with that value. So this is the area where that is observed. Elsewhere, it's not observed. So we'd have to look at the density values and the flow values. But just from the fact that this interface is sloping with the opposite sign, it's indicative that the geostrophic breaks down right over that area. Okay, so now I'm going to show you real data to see how those would compare to the slope predicted by Margulis relationship. So we go back to the Chesapeake Bay. There's a Chesapeake Bay, and we have a transect right here. This is amplified here. So we're going to be sitting here in the ocean looking into the estuary, and we're going to look at two examples of density distributions across this section. And these are average over several tidal cycles. All right, so again, we're sitting in the Atlantic Ocean looking into the Chesapeake Bay. And you have one picture that represents an average at the end of April, and this is another picture in the summer, July, mid-July, more or less. So you can see here that the lower salinity, which is a proxy for density too, 21, 22, 21, 20. It's around 20 here, and the greatest is 29. And then here, the lowest salinity is 24, and the greatest is 30. So it makes sense. Does it make sense that the isohalines are tilting like that? Does it make sense that they're tilting like that? Does it? Yeah. So the fresh water is coming out on this side, and the saltier water. Notice here that the saltiest water is here because of the greatest depth is there. So we will also cover that later on. But anyway, the slope is like that. But also notice that the slope changes. It is sort of mild here, but it's much greater here. Same here. It's a little higher than here, but it changes dramatically over this area. Okay, so I'll come back to this and ask you why do you think that is. So I'll start thinking about that. So let's take this example. And just from other measurements that we have, we can say that the outflow in the upper layer can be represented by a value of 10 centimeters per second, and the inflow in the lower layer can be represented by a value of 5 centimeters per second. The density, the nominal density for the upper layer is 1017, and the density of the lower layer is 1022. The Coriolis parameter is 8.8 times 10 to the minus 5. So the Margulis slope that we obtained from these values is 2.7 times 10 to the minus 4. How would you determine the slope of this slope? So maybe like that. It's approximately, that line approximates the slope, at least in the channel. So we have 2 meters over 8 kilometers. And that's 2.5 times 10 to the minus 4. So that's close to the slope predicted by Margulis. But here it's much greater, right? So again, I'm going to come back to this and ask you why. So right here, the exchange flow was a little less sheared vertically. The outflow 8 centimeters per second, the inflow 6 centimeters per second. With the upper layer 1021, lower layer 1023, and the Coriolis parameter the same. That gives us a slope of 6.4 times 10 to the minus 4. And the observed is actually greater, 8.8 times 10 to the minus 4. Same order of magnitude, actually pretty close also. So we can almost safely say that in the channel, the momentum balance is almost geostrophic. We can safely say that. But how about elsewhere? Look at here. The isohalines are practically vertical, and here they're much more steeper. Why is that? What do you think makes the isohalines? What would be obvious to think that instead of the isohalines being like this, you make them vertical? What would cause that? Mixing. So there's much more mixing over this area than over this area. Why do you think there's more mixing over this area? Most markedly over this area than over this area. You see, over this area is vertically homogeneous. Why do you think there's more mixing here than here?
Slower velocities.
Slower velocities where? Here?
No,
Here? So if there's lower velocities, you would expect weaker shears and less mixing. Weaker vertical shears, right? The slower the flow, the weaker the vertical shears produced by bottom drag. So there's more mixing here than here, right? Because it's shallower. The bottom effects affect a greater portion of the water column here than here. So the slope there, the greatest slope means that there's more mixing. So we have a departure from geostrophy. Geostrophy doesn't apply over this entire section. So it's almost as if we had two different estuaries right there at the entrance. One that's in geostrophic balance in the channel, and one that is strongly frictional over the shallow area. So this is something to consider. It's quite interesting. Now, could you draw the pressure field associated with this salinity? You think? You can think of the flow field and think of the cartoon that we drew at the beginning, and you should be able to draw. So this is actually part of the homework that I'm assigning today. I'll tell you about it at the end of the class. Okay, what happens when the flow is in geostrophic balance or near geostrophic balance? We have here a space shuttle's photograph of this tributary to Chesapeake Bay. This is the James River, and this part here is the lower Chesapeake Bay. This is the lower Chesapeake Bay, this is the James River. So you can see, what is this, you think? You see this here compared to that? The color here compared to that color. And look at that, the color of the water here compared to the color of the water here. What do you think is going on? You have fresh water carrying sediment. Right. So you see highly turbid water here, very well defined, the water from this tributary. So you can see that as the outflow forms a bulge here, just like when you blow on a candle, it goes sort of bulgy, it forms eddies, right? It forms eddies, so the water is blown through this constriction and forms this bulge-like structure, but then it forms this coastal current, or this outflow region. What do you think constrains that? Oh yeah, it says there. That answered my question, the question that I was going to ask. So the outflow modified by rotation, okay, will be restricted by the internal radius of deformation. So this is restricted by internal radius of deformation. And you can derive it from geostrophy. If you can simplify the geostrophic balance with this relationship, if you scale it, this term can be scaled, the velocity can be scaled as a length scale divided by a time scale, and the time scale is f, so it's L times f. The velocity can be scaled as L times f, that's why you have f squared L. So the acceleration term can be scaled like that, where L is the length scale that restrains or constricts this flow. And then on the right hand side, you have G prime, which is G delta rho over rho. That's G prime. This delta X is the length scale that we're talking about, and this Z can be scaled by the depth of the water column. So if you solve for L here, this is the length scale that we're looking for. So the length scale equals, look at that here. Part of your morning sayings, it comes here. It appears right there. So the length scale, this length scale that's constricting the outflow, is the square root of G prime H divided by the Coriolis parameter. And this is called the internal radius of deformation, or the internal Rossby radius. So notice how it remains sort of constant here. And that's because when it's in geostrophic balance, it's constrained by that length scale. The speed of the internal gravity wave, long internal wave, divided by the Coriolis parameter. And so this is an important concept to keep in mind. That's the internal radius of deformation, or the internal Rossby radius.